All right, so welcome back, everyone. We're going to hear three talks, but I think we first had an announcement from the organizer. So please go ahead.
Yeah, absolutely. So in case you missed it, the Gong Show today is starting at 10 past 4. So a little bit of a change of a plan because we have too many participants. And also I wanted to announce that today at 3:30, please, all the speakers from all the sessions today, there's going to be a photo for the speakers outside. So 3:30, this is after the last talk today. And also members of the Universe Plus collaboration, there's also going to be a photo at 3:30 as well. So please be there outside of the tent. Okay, so with that.
All right, thanks for that announcement. So now we're going to hear three talks, and we're going to start with Hayden Lee, and he's going to tell us about kinematic flow and the emergence of time. Please go ahead.
Is this working? All right. So I'd like to thank the organizer for the opportunity to present us work at this wonderful conference. It's my first time at Amplitudes. So my background is in cosmology. So in case you're wondering about the title, I'll be talking about cosmological correlators. So not exactly on scattering amplitudes, but in recent years, we've been seeing many fascinating connections between these two fields. So I'll be highlighting some of them in my talk. Specifically, I'll be talking about some interesting hidden pattern that we have discovered in the kinematic space of cosmological correlators, and hence the origin of the title, and see how the physics of time evolution seems to emerge from this interesting pattern. So hopefully by the end of the talk, you will be understanding what this picture is supposed to represent. All right, so this is based on these recent papers that we wrote together with Nima, Daniel Bauman, Aaron Hillman, Austin Joyce, and Guy Pimentel. Okay, so since this is a conference on amplitudes, not on cosmology, let me begin with a big picture and explain what cosmological correlators are and why we care about them. So one of the fundamental questions we want to address in cosmology is what is the origin of structures in the universe? And we try to understand this by measuring correlation functions that we can see on the sky. So for instance, we can see that the densities of galaxies on the sky are correlated as a function of the spatial distances separating them. And similarly, if you look at the cosmic micro background, the background temperature is not perfectly uniform on the sky, but there are cold and hot spots in the universe. And these are correlated as a function of the angular separations on the sky. And modern cosmology is essentially a study of these types of correlation functions. So from the detailed pattern that we see in these correlations, we can infer the physics of the primordial universe. And the way we go about doing this is that we measure these late-time correlation functions and trace them all the way back to the very beginning of the hot Big Bang. And there we see that there's a spatial surface called a reheating surface that encodes the initial conditions for these late-time correlation functions. And importantly, this is not exactly the beginning of time. And in the standard picture, we think that this initial condition was generated from a preceding period of accelerated expansion called inflation. Okay? So you can think of this surface as corresponding to the end of inflation in the preceding period, or the asymptotic future boundary of a quasi-de Sitter space. Okay, so now the question is, what is the initial condition, and what physics generate this initial condition? So what do we currently know about this? Currently it turns out that all that is needed to explain the current observation is just a very simple two-point function in this initial condition, and this happens to very nicely agree with the predictions of inflation. Okay, so this is very good. However, it turns out that the information contained in the two-point function is essentially just kinematics. It's just given by the free propagator. Okay, so in order to really learn about the dynamical content of the theory, such as the particle spectrum, their interactions and scattering, and so on, they're all contained in the nonlinearities of the theory that generate higher point correlation functions. Okay, so in order to really learn about the detailed physics of inflation and the origin of structures in the universe, we really need to go out and measure these higher point functions in the sky and understand their theoretical properties. Okay. And now is very timely to pursue this study because next decade is going to be a very exciting time for observational cosmology. So we're going to have a whole array of new generation of galaxy surveys that will measure this correlation function in the galaxy distribution in detail. That will go beyond the precision of the CMB measurements that have been the state of the art for a long time. Okay, so just to give you a rough sense of the numbers involved, so here. For certain class of inflation models, the next generation of galaxy experiments will bound this size of the three-point function for inflation by an order of magnitude better than the current CMB constraints. So we will have much larger access to the theory space of inflation in the coming decades, which is very exciting. And Misha will probably talk about it in his tomorrow's talk. Okay, so next decade is going to be very exciting with lots of observational data. At the same time, it is essential that we also gain a better theoretical understanding of these correlation functions. So ideally, we'd like to understand these properties and structures sufficiently well so that if we given any measurement of this correlation function, we would like to fully reconstruct the physics of inflation by just looking at the patterns that we see in these observed correlations, which exist on the boundary of inflation spacetime. Okay. So obviously, we don't get to directly measure and see what happened during inflation, but only get to measure its output. Okay. So the big question I would like to understand is what really governs the patterns that we observe in these correlation functions that exist on this boundary surface. And I'm guessing that this question will resonate with many of you in the audience because this is the type of question that arises in the modern study of scattering amplitudes. And especially over the past decade, we have seen a radical reformulation of scattering amplitudes in terms of more abstract combinatorial and geometric ideas, which are giving important insights into these foundation questions. So one of the important concepts is positive geometry, as we heard in this morning, which is a certain class of geometric spaces which have well-defined volumes that directly give the amplitudes in terms of the boundary kinematic data, whose properties encode the basic underlying principles of quantum mechanics of relativity. Okay, so this is an indication that there's a fundamentally different way of getting this basic physics involving the unitarity and locality of space-time in terms of more fundamentally combinatorial and geometric ideas that might underlie the scattering amplitudes. Okay, so clearly this boundary way of thinking about the problem has been highly influential in the study of scattering amplitudes. So motivated by this, we'd like to ask similar questions in cosmology. So whether there exist some novel mathematical questions formulated directly in the boundary kinematic space, whose answer is going to be these correlation functions that exist on this boundary surface. Okay, so I need to admit that our current such an understanding in cosmology is still very primitive. But in recent paper, we think we might have seen some possibly first glimpses of such interesting structures in cosmology. So I'll be excited to tell you about this story in the rest of the talk. Okay, so here's the outline. So first, I'm going to tell you a more precise definition of cosmological correlators and explain how these correlations can be written as certain integrals called twisted integrals, and then tell you how we can go about solving these integrals. And next, I'll tell you about some interesting hidden pattern underlying the results and show how the entire problem solving this integral can be formulated in terms of combinatorics. And finally, I'll conclude. Okay, so let me begin with the first part. Okay, so we have studied this correlation function in the context of a certain toy model. Okay, so here's the toy model that we studied. So this is a model involving a conformally coupled scalar, okay, and with a non-conformal phi-cube interaction. So obviously, this simple model doesn't quite describe our integral universe. However, it turns out that the result in the theory can be used as a useful input for the calculations for the actual observable correlation functions that we can see on the sky. So understanding this particularly simple theory is actually very helpful as a first step. Okay, so we will study this theory. In particular, we'll study this theory in a general FRW spacetime expanding as a power law. Okay, so here's the metric in conformal time, and A is the scale factor that expands as a power law in eta, and epsilon here is a parameter that parameterizes different expanding backgrounds such as de Sitter, flat space, radiation, matter-dominated universes. So here we're going to be completely agnostic about the background evolution and not assume that epsilon is necessarily small as in inflation or take any of these special integer value, but treat this epsilon as a completely general parameter. Okay, so that's the setup. So specifically, the object we will be studying is the tree-level cosmological wave function in this theory. Okay, so first some terminologies. So in cosmology, we sometimes like to make the distinction between the wave function versus correlators, where the latter quantity is obtained by integrating over the square of the wave function, just as in quantum mechanics. So this is somewhat similar to the distinction we make between amplitudes and cross sections, where the latter quantity is obtained by integrating over the square of the amplitude. Okay. So in this sense, the wave function is a slightly more primitive quantity that we can study compared to correlation functions. So this is the object we will study first. Okay, so here I've shown some representative Feynman diagrams that we'll study. And these wave functions are related at this future boundary surface at eta equals 0. Okay? And the kinematic data that labels these various wave functions are given by these certain energy variables that I'm calling x's and y's. So x's label the energies associated with the vertices, and the y's label the energy associated with the internal edges of these graphs. Okay. All right. So in the standard picture, the way we go about computing this wave function is by performing some time integration over some various propagators, going all the way up to this eta equals 0 surface. In particular, there's a one-time integration that we have to do for each interaction vertex. So that means that as we go to higher points, we're going to get a multi-layer time integrals that we need to do even at tree level. Okay. So this is a very complex integrals that we have to do in general. However, in flat space, things are particularly simple, and it turns out that the wave function in flat space is given by some simple rational functions with simple poles in the denominator that label their singularities of the wave function. Okay? And in particular, there's a very nice combinatorial method of getting this wave function directly. So the way to derive this is to take these Feynman diagrams and truncate all the external lines, and then we start drawing tubings around these vertices. And to get the wave function, we basically have to take the total energies that is enclosed inside each of the tubings, and then take the product in the denominator, and that gives the flat space wave function. Okay, so this suggests that there's some nice connection between this cosmological wave function calculation and combinatorics and these graph tubings. And later on, I'll explain that generalization of this story will play a crucial role in this calculation of the actual FRW wave function that we want to compute. All right, so let me now show you the expression for the FRW wave function in this theory. Turns out that because of the conformally coupled scalar that we're dealing with, it turns out that this wave function in FRW can be expressed as a certain integral over the previous flat space result. Okay, so here I've written in this general form where U here is the so-called twist factor that includes this epsilon deformed measure, and omega psi is the rational differential form that comes from the flat space wave function that we computed, whose argument is shifted by this little x variable that it integrated over, and there's a one integral we have to do for each vertex over 0 to infinity. Okay, so this is a very concrete expression for the FRW wave function that we can try to study and compute, and this falls into a type of integrals called twisted integrals. And you might recognize that this written in this form, this wave function integral looks very similar to the type of integrals that we do for scattering amplitude at loop level in certain representations. So we can borrow all these interesting and advanced techniques that has been developed for amplitude calculations over the decades and more. These include things like twisted cohomology and the method of differential equation that we've been hearing about from this different talks throughout the conference. Okay. And not surprisingly, this technique can be also useful for studying these cosmological correlator calculations. So let me explain how we go about doing this. So first of all, what is twisted cohomology? So this has to do with the fact that the total differential of this twisted integral actually vanishes. Okay, so this is the total differential, and you can write this in a way as a covariant derivative, a certain covariant derivative acting on the rational form omega. So that means that anything that differs by this covariant derivative at the level of the integrand actually gives us exactly the same integral upon integration. Okay, and twisted cohomology is just a fancy name for the set of equivalent classes of these integrands that differ by covariant derivative and giving the same integral. And a slightly lowbrow way of saying the same thing is that this basically counts the number of independent integrals in a given vector space of a given integral family. Okay, so what's nice about this framework is that it gives us access to a powerful theorem that allows us to do this counting for us in a geometric way. Okay, so the theorem states that the size of the basis for this vector space is given by the number of bounded regions formed by the singular hyperplanes of this integrand. Okay, what is very nice about this is that if we know that the basis is finite, then it automatically implies that the given basis satisfies the closed system of differential equation, as has been reviewed in many talks throughout the conference. Okay, so this automatically implies that the twisted integrals that we're dealing with are guaranteed to satisfy differential equations. Okay, so let's now see how this gets applied to our cosmology problem. So we'll be looking at this simplest non-trivial example of two-side chain, which is equivalent to the 4-point function at tree level. So this has two vertices, so we can write it as a two-dimensional integral over twist multiplying the deformed flat space wave function that we saw before. Okay, And now we want to enlarge this system to consider a family of integrals with the same singularities of the original integral. Okay, so now I've defined this omega as the most general two form, rational form that has these singular factors in the denominator raised to arbitrary integer powers. Okay, so these are the same singularities as the original integral, where I've labeled T1 and T2 as the twist vectors, and these are B1, B2, B3 labeled the three singularities of the original wave function. Okay. All right, very good. So now the zeroth order thing that we should determine is the size of the basis for this family of integrals. And we can use theorem to do this. So basically, we can count the number of bounded regions from this singular by this singular hyperplanes. In our problem, we have these 5 singular factors, and 4 of them form this square. And then there's one diagonal line here. So in this picture, you can easily count the number of bounded regions. There are 4 of them. So that immediately implies the dimension of the vector space is 4. Okay? So we have 4 independent master integrals. All right, so in principle, we can choose any of them to be our basis, but it turns out that there is a particularly convenient choice that is given by the so-called canonical forms of these bounded regions. Okay, so the canonical form is defined to be a differential form that has logarithmic singularities on this boundary and no singularities elsewhere. So for example, for a triangle, it satisfies this, it is given by this particular formula. So I'm going to choose as our basis just the 4 different triangles formed by these regions. Okay, so I'm just gonna give some names. So omega psi, omega f tilde, omega z. Okay, and omega psi is the canonical form that gives the original wave function. Okay, so because we are computing the wave function, we're gonna just include it as a part of the basis. Now the key next step is to take the differential of this basis vector and then use various IBP relations to derive the differential equation. And this is the final form that we get. So on the left, we are taking the differential with respect to kinematic variables. And thanks to the choice of the basis, we have this nice epsilon factorized form. And A is a 4x4 matrix that takes the explicit form. Okay. And with the constant matrix, multiplying the D-log forms. And we are calling the argument of these D-log forms as the letters. Okay? So this is a concrete expression that we get. And this should be very familiar to the people in the audience working on related problems for scattering amplitudes. And you might think that we can just continue to use the standard method to work at this higher point functions. However, it turns out that this method actually breaks down if you're being naive about this, and this is due to the following 2 reasons. So first of all, twisted cosmology actually gives the most general counting for this generic hyperplane arrangement, whereas our cosmological integrals are actually highly non-generic. Okay, so it actually satisfies a much smaller size of the basis with a less number of singularities. Okay, so we have to be somewhat careful about the choice of the basis here. And secondly, the challenge is that deriving differential equations typically requires using many integration by parts identities, as we heard from the other talks. And typically, this is the major bottleneck of applying this technology to higher loop amplitudes, where the size of the system becomes really large. Okay? And initially, when we faced with these challenges, we couldn't also go much beyond the 2-side example that I showed you. But it turns out that after working on this for a couple of years, we've discovered some nice pattern underlying these differential equations that basically allow to derive the expression for arbitrary tree graphs by drawing some pictures according to some graphical rules. Okay? So this is the story that I want to tell you in the next part. All right, so this is the concrete expression for this 2-side example, the differential equation for the 2-side example, where the A matrix had this particular form as constant matrices multiplying these various D-log forms. Okay, but just by looking at this entry, it wasn't totally clear what the underlying principles were, what the underlying structures were, and the entries of the matrix looked more or less random numbers. Okay, and this was even more true for if we look at the higher point function examples. However, something interesting happened when we drew pictures of the result, and a hidden pattern was revealed when we did this. So let me explain what we did and what happened. So basically, all the entries of this A matrix consist of these D-log singularities, which are some combination of these X and Y variables. Okay? And there's a one-to-one mapping. There's a natural way of representing these various singularities in terms of these tubings of the graphs. Okay? So here I've shown some examples. So the D-log singularity of the X1 variable has this tubing of the left vertex, and so on. Okay, and so we can represent all of the entries of the matrix in terms of the graphical tubings. Okay, and what happened is that this reveals some nice pattern among the entries of the matrix. Basically, there was some sort of a directed growth that happens as we go from the first entry of the matrix to the last entry. Okay, so starting from some simple tubings from the first entry, basically as you go down the columns and rows of the matrix, these tubings grow in a very specific way. And when the tubing fully grows to enclose the full graph, this is the point where the differential equation closes. Okay. So some simple set of graphical rules allow us to predict all the entries of the matrix by just drawing some pictures without using any IBP relations in the end. And if you go to higher points, the system becomes pretty complicated. So this is the example for the three-side chain or the 5-point function at tree level. And naively, the matrix entry is really complicated, but exactly the same rules apply that predicts the entries of this matrix. Okay, so starting from the first entry with these simple tubings, they grow in a specific way, and then the system closes when the tubing fully encloses the graph. Okay, so what's nice about these graphical rules is that if you ask me or any of our collaborators to reconstruct the whole matrix in real time, I think we can do this. So this is the graphical rule that we have found in this differential system. So let me give you slightly more detail about this, what this graphical representation is really about. So we have two ingredients in our differential system, which are the letters and the functions. Okay, so our functions also have some nice graphical representation in terms of this disconnected tubings, and the letters are represented by these colored tubings, which are some connected tubings. And just to distinguish these two types of tubings, we color the tubings for the letters and then call them activated. And what's nice about this tubing rules is that we can automatically get all of the entry, all of the physical letters of the wave function, and also the function that contribute to the minimal size of bases. Okay, and in particular, there are 16 of them for this three-side example, and which is much less than the naive counting that we get from this counting all the bounded regions in the three-dimensional space, and this becomes even better for the foresight, where we're comparing 64 versus 201. So it was really crucial for us to work out this physical basis, canonical basis, where things simplify and then they satisfy nice graphical rules. Okay, so let me finally show you what these rules actually look like. Okay, so I'll be very schematic, but if you want more details, just find me offline and happy to explain the details. Okay, so the general rule is that the tubings always grow when we take the differential of it. Okay, so for example, if you take this particular tubing, okay, and then you try to take the differential of this guy, what happens is that we simply activate all of the tubes around these individual vertices. Okay, so when we do this in the first step, we get these three types of letters corresponding to these colored tubings. And what happens next is that these tubings always grow to enclose the cross in the intermediate cross next to it. Okay, so in the process, these tubings can grow, or it can even merge with the existing tubings, or it can absorb another tubing. Okay, and basically this four phenomena, activation, merger, growth, and absorption, basically constitute all possible ways in this graph tubings can grow for arbitrary tree graphs that we have considered. Okay. So in the way we have defined these graphic tubings and the growth rules, this has really no obvious connection to the original time integrals that we started with. So this seems to have, this graph tubing seems to have a life of its own. And it was interesting for us to recasting all of the ingredients in this graphical language reveals some interesting pattern in this system. All right, so that was the abstract. So let me now conclude. Okay, so just like in the case of scattering amplitude, it was interesting that the differential equation technology was very useful to understand the structure of this FRW wave function that we have studied in this toy model of conformally coupled scalars at tree level. And beyond this, just getting the result out of the differential equations. So usually differential equations are just effectively just a tool for getting the results. But it was interesting for us that correlators actually had a physical interpretation for these differential equations. So there was a simple set of rules that allowed to predict all the differential equations and predict all the entries of the matrix equations using some simple set of rules. This works for all tree graphs. All right, so in the last slide, let me quickly mention some of the interesting future directions that we can pursue. So obviously, the analysis that we have done is restricted to this particular toy model. And for phenomenological applications, it will be important to generalize this story to more complicated and other types of graphs, such as those involving massive particles and also loop diagrams in cosmology. And lastly, let me mention that even though we find this interesting pattern in the differential equations, we don't have a first principle understanding of where the rules actually comes from. Okay. But in this business, if you have discovered this kind of hidden simplicity or structure in the system, almost always it implies that there's some underlying structure that could explain this pattern. Okay, so it will be extremely interesting to see whether there's some sort of a underlying geometric structure or positive geometry that can explain the patterns that we have found in the system. Okay. So overall, I think this presents a very interesting connection between scattering amplitude and cosmology with lots of future avenues for future exploration. Okay, so I'll stop here. Thank you for listening.
Thanks, Hayden, for a very interesting talk. So now there's time for questions. So maybe we start here.
Yeah, so if I understand correctly, your model is working after the recombination, right? Is that?
So these correlations are actually before recombination. So right after inflation. So we're computing the correlation function from inflation or any early universe scenarios that generate these initial conditions.
So this is for initial conditions. Yeah. Okay. So is this a correlation for matter correlations or for CMB?
Yeah, so we are imagining that we are computing the inflaton correlation function, so massive scalar fluctuations from this initial period. And then these can evolve into the future and then generate these CMB fluctuations. So what we are doing is we are computing the density correlation functions, okay, in this initial time. And then this density correlation function can generate some different types of correlation function in the late universe, for example, the CMB fluctuations, in the temperature fluctuations, or a density correlation function in the galaxy distribution. So there are many different types of correlation function you can look at in the late universe, but the underlying, what's underlying it is this initial condition, which is generated from pre-Big Bang, pre-Hubble Big Bang.
Thanks.
All right, then there was a question in the back.
Hi, very nice talk. I had a question about the size of the matrices. So this is smaller usually than the size of the number of master integrals, and you're usually considering like submatrices, like block basically that are smaller. I was wondering if you have a understanding combinatorial of the dimension of these matrices. Also considering that your definition of tubings is not the canonical definition in the mathematical literature. So I was wondering if you knew how this size scales or what's a combinatorial interpretations of the size of the matrix.
Yeah, that's a very interesting, very good question. So yeah, so the way, so I skimmed through this in my talk, but the way we define this tubing for the functions, for example, we are defining them as the complete tubings of these graphs. So by complete, I mean that all of the vertices, you can't quite see this little circles here on this slide, but there's a little circles encircling all the vertices. And you can, in this way of defining things, there's a interesting hierarchy between the functions where in this column, all the functions include just one cross in the middle. And in this column, these tubings include two crosses, and in the last column, they include all the crosses, as well as the vertices. And there's an interesting combinatorial problem you can solve, and actually the size of basis, if you go to larger systems, it basically grows as a power of 4. So you get 4, 16, 64, and so on. And so it's a different, so it's a slightly modified definition from the standard tubing picture that mathematicians consider, where we have this extra marking for the internal edge. Actually, we spent quite some time trying to find some definition of this tubing picture in the mathematical literature, but we couldn't. But I think this is an indication that this is a very interesting object to study further.
All right, I think there was one or two questions here. Yeah.
You can go. Oh, okay. Yeah, so you know the weight shifting operators and the other differential operators have been derived in the bootstrap literature. Do they commute with the differential operations that you're doing here in terms of activation and stuff?
Let's see. So weight shifting operators are defined in this De Sitter limit, right? Because weight shifting operators, for those of you not familiar with the weight shifting operators, there are some certain differential operators that is conformally invariant that can be used to shift the masses of the scalar field in De Sitter space. So if you take the dissimilar limit, I think, yes, if you take the dissimilar limit carefully first, and then differential equation should commute with its operators. But I think you have to take the limit first, and then apply this operator, because taking this limit is actually quite subtle. If you naively think of taking this epsilon go to the limit, the brightness vanishes, but actually that's not the case, because some of the functions in the spaces actually scales with epsilon inversely. Okay, so actually what happens when you take this epsilon go to zero limit, all the diagonal entries actually vanish because they're just proportional to themselves. But then the off-diagonal entries are, some of them are non-zero, and some of the functions actually become just constant in this particular limit. So the matrix actually becomes much simplified in this particular limit. And once you have taken this limit properly, I think you can commute with the observational operators.
So, sorry, yeah. So my question is two-part, I guess. One, is there any obstruction to doing tubings for more complicated topology? Let's say you have a vertex kind of diagram. Like I saw like all of the diagrams that you had were like one, like 4-side, 5-side.
Yeah, so yeah, exactly the same tubing picture holds for this different types of graph that have like a star topology or more interesting topology. Basically, our understanding is that why this works for arbitrary tree graphs is that this growth of tubing picture is really local, right? So this particular growth of the tubing, activated tubings, only grows locally around this activated vertex. So it doesn't quite matter what kind of complicated topology you have in the other part of the diagram, the growth is always local. So if you were to look at the differential system for the larger matrix, you will find a subsector which is really given by this smaller growth picture that comes from the smaller side example.
And you know, like you're talking at the level of the diagram right now, can tubing give any intuition about the sum of all diagrams?
Yeah, so here, yeah, very, very good question. So here we are talking about just a single Feynman diagram, okay? So even for a single Feynman diagram, we have to deal with this integral, so therefore this differential technique is useful. Now we can think about the sum of a diagram. So this is closely related to this trace phi cube theory that Kevin talked about. So in that picture, this tubing of a graph really becomes a particular triangulation of a kinematic polygon, okay? And there's also a nice generalization of this tubing picture to this sub-polygons of this triangulation. So that's something also we want to understand in the future.
All right. I see there's a question here, but let me also sneak in a question from myself. As the chairman, I take the opportunity. So maybe you can say a few words about how will you include tensor modes or graviton amplitudes? Is that something you thought about?
Yeah, so yeah, generalization to higher spins would be extremely interesting. So from inflation, we have two types of observable, which is the density correlation function and the gravitation waves. So very naively, if you think about computing graviton correlation functions by Feynman diagrams, you will have many different Feynman diagrams, and each of them will be accompanied by certain tensor structures. So very naively, you can at least apply this technology to individual Feynman graphs that contribute to the Feynman diagram computation for gravitational waves. But obviously, it will be much nicer if there's a way to see that if you combine all of the different diagrams for the gravitational wave, we see some nice simplified structure. So we don't have that kind of example in cosmology yet, unlike for scaling amplitudes. But it will be very interesting.
So the last question from Lance, and a very quick question, hopefully.
Okay, thanks. Just a simple question of how much did you test this pattern against the actual, you know, in particular, if you go to a new topology like this star, were you able to check it directly?
Yeah, we were able to check for I think we went up to something like 8-side graphs. And then, so we also developed a completely algebraic algorithm for deriving these different equations. And then we checked up to some 8-side graph with different topologies.
Okay.
So we were pretty confident that this should work.
All right, we're running out of time, so let's thank Hayden again.